Welcome back, pre-calc. It's good to see you guys. We're going to continue on with some trigonometric identities, what we were working on yesterday or in the previous video. But here we're going to talk about sort of a different trigonometric identity that I really want you guys to have memorized. And this is based off of the unit circle. So this is called the Pythagorean identity. And let me go ahead and show you where this comes from, and that'll hopefully help you guys remember where it is, or at least where you can sort of remember to derive it from. We've been doing derivations in class. So say we've got a unit circle. It's going to look something like that. Unit circle, if we remember from the unit circle, no matter where we are on the unit circle, right, part of the thing that makes it the unit circle is the fact that the radius is always 1. So out here, I'm at 1, 0. Up here, I'm at 0, 1, all the way around, right? So I know that the radius right here, r, is going to be equal to 1 always. Now, if I take a little bit of a closer look at this, you guys can figure this out really quickly, this identity anyway. So if I just drop a line right here, say I've got some point right here, I'm just going to call it x, y, right? And I've got some angle right here, theta. Well, I know that x, y, right, if I think about this as a triangle, right, I'm just going to blow it up really quickly here. So here I've got theta. This, my base right here, is going to be equal to x, right, because I'm starting at the origin, and I'm going out this distance, which is going to be x, and then I'm going up this distance, which is going to be y. And I know what this is right here. This is 1, right? That's going to be my radius, which is 1. So I've taken the unit circle and I've sort of broken it up into what the coordinates are here. Coordinates are here based off of this theta, based off of this angle. Well, I know what x is equal to, right? X is going to be equal to the cosine of theta. So I know that x, this distance, is going to be equal to the cosine of theta. Now I know that y, this distance right here, is going to be equal to the sine of theta. And I know this because this is the very definition of the unit circle, right? So the sine and the cosine of this angle are just going to give me my 2 coordinate points right there. Now if I input this, my x and my y, into my Pythagorean theorem, right, this is going to be a right triangle. So I can say that x squared, I know that x squared plus y squared is going to be equal to 1. Now if I plug in sine and cosine here, so instead of x squared, if I say cosine of theta squared plus the sine of theta squared is equal to 1. So nothing terribly groundbreaking here, just basically taking whatever it is for x right here, plugging it in. Now, of course, we've got to rewrite this, and once I can never figure out why they always, with these trigonometric ones, why the squared always is written like this, whereas cosine squared theta. Have no idea, but this is just sort of the convention. Sine squared of theta is equal to 1. And this is the identity. I'm just going to switch the sine and the cosine around because that's typically how it's written. But the identity that I want you guys to have memorized is sine squared plus the cosine squared is going to be equal to 1. This is the important one right here. This is where everything is based off of. And sure enough, we were able to derive it right from the unit circle. So sine squared plus cosine squared is equal to 1. Now there's a couple other identities that we can figure out, we can derive from here that involve the tangent, the secant, the cotangent, and the cosecant. But you can all derive them really easily from here. And so let me jump into an example here of when you would use this. So the example is, I'm going to give you that the sine of t, or the sine of theta, is going to be equal to 3/5. And I want you to find the value of, you're told to find the cosine of theta. That's it. That's all the information you're given. Right? So cosine of theta is equal to what? So that's totally fine. I've got this equation. I know that sine squared plus cosine squared is going to be equal to 1. So I can just plug things in. So I know that sine theta is equal to 3/5. So I can say 3/5 squared, that's sine squared, plus cosine squared is going to be equal to 1. Well, 3/5 squared, this is going to be equal to 9 over 25. So 3 squared over 5 squared is 9 over 25. Plus the cosine squared of theta is going to be equal to 1. Now I'm going to subtract 9/5 from, or 9 over 25 from both sides. That goes away. I end up with cosine squared theta is going to be equal to, if I do this subtraction here, I end up with 16 over 25. And now in order to get the cosine by itself, right, I'm looking for cosine, not cosine squared. To get the cosine by itself, I'm going to take the square root of both sides. So on this side, I end up with the cosine of theta. And on this side, the square root goes to the top, the square root goes to the bottom. Square root of 16 is going to be 4. And the square root of 25 is going to be 5. So the cosine of theta is going to be equal to 4/5. Not too bad. Now, the other thing that I'm going to talk about, the other thing I'm going to talk about in the lecture today is periodic functions. Now, periodic functions are super cool. And it relates back to, if you remember when we were talking about coterminal angles, this is exactly where coterminal angles come into play. Periodic functions. And so if you look at the unit circle, right? So I've got this circle here. We'll call this my unit circle-ish. It's a little bit lopsided. So if I start here, say I start at some point right here, right? Some generic point. I have no idea, or I say I know what this angle is, right? So this is going to be some angle theta, but I'm at this point. If I start traveling around my unit circle, right? So I take this point and I move it back all the way around my unit circle, advancing it forward, right? So in the positive direction. If I go all the way back around, I can say that theta, and I end up back at the same point, whatever values I have for x or y or tangent or whatever, as long as I'm back at that same point, they're going to be exactly the same. So if I look at theta, right, I can say that theta is going to be the same as if I just went to theta and I added one full revolution, right? So I can say theta is going to be equal to theta plus one full revolution is 360 degrees, or, since we're dealing in radians, or 2 pi radians. So theta is going to be equal to theta plus 2 pi. This is what a periodic function means. And this shows up all over the place. All over the place. Sound waves, any sort of waves, any sort of thing that requires repetition, like a motor turning, a gear turning, right? Something that's going around in circles. If you want to think about the amount of daylight throughout the year, right? It follows a very cyclical periodic function, where if this is the amount of daylight in hours, right? And this is the time of the year in months, right? So from January to February, January we don't have very much daylight, so I'm going to start it off down here. And then we go back up to, say, July, right? July we've got tons of daylight. We come back down to January, December 21st is a solstice, it goes back down, right? So this is summer, lots of daylight. This is winter, very short daylight. Sure enough, right? So that's the end of that year. And then when we start off again in January, it's going to go back up, right? So we're following this periodic function. It's something that repeats itself. So it doesn't matter if we're in the summer this year or the summer this year, we're going to have pretty much the same amount of daylight. Or the winter here and the winter here, we're going to have pretty much the same amount of daylight, even though it's different years. Same thing with periodic functions. So here I'm starting here. It doesn't matter if I'm here or if I'm one revolution around, I'm still at that exact same point. So basically what this means is if I have a function, say f of theta, and it's going to be equal to f of some theta plus some amount. In this case, it's going to be pi, or 2 pi. 2 pi. Then I have a periodic function. This is the definition of a periodic function. Now this one is specific to the unit circle, of course, which is the most common one that you'll run into. Now what you'll notice with sine and cosine is the sine and cosine are periodic functions. Just like the sine is an even function and the cosine is an odd function. Or sorry, I got that the other way around. Cosine is an even function and sine is an odd function. The sine of t is exactly equal to, or sine of theta, is exactly equal to the sine of theta plus 2 pi. And you can plug this into your calculators, right? So say I plugged in, let's start off simple. Let's say 0. Say theta is equal to 0. So if you plug in this, let me rewrite this. If you plug in the sine of 0 into your calculator, and then you plug in this case, the sine of 0 is going to be equal to 0, and you plug in the sine of 2 pi into your calculator, you're also going to get 0. Well, the cosine is a periodic function as well. So you can say the cosine of theta is exactly going to be equal to the cosine of theta plus 2 pi. So you can do the same thing here. So cosine of 0 is going to be equal to, in this case, it's going to be 1, and the cosine of 2 pi is going to be equal to 1. Well, why stop there, right? It's periodic functions. So if I plug in 2 pi, or if I say theta is equal to 2 pi, so I can add another 2 pi on top of it. So sine of 4 pi. I don't even need to look at it. I know it's going to be 0. Same thing with cosine. The cosine of 4 pi is going to be equal to what, class? I'm not hearing you guys. Right. Oh, there you go. It's going to be equal to 1. Bingo. Now, what does this come from, or how does this relate to coterminal angles, right? So say I gave you, I want you to find out what the sine of 9 pi over 4 is. Sine of 9 pi over 4. First thing you need to notice is, hey, 9 pi over 4 is greater than pi over 2, or 2 pi. So in order to simplify this, I can say the sine of 9 pi over 4 is going to be equal to the sine of 9 pi over 4. And whether I'm adding or subtracting, it doesn't really matter. So I know it's going to be equal to, sine of 9 pi over 4 is going to be equal to the sine, I can rewrite this as pi over 4 plus 2 pi. Now where did this come from, right? Where did this pi over 4 plus 2 pi come from? So I know if I have 9 pi over 4 and I subtract 2 pi from it, this should look familiar with coterminal angles. 9 pi over 4 minus 2 pi is going to be equal to 9 pi over 4. Then I'm going to convert this 2 pi into something with a denominator of 4, so it's going to be 8 pi over 4. This exactly is equal to 2 pi. So 9 pi minus 8 pi is just going to be equal to pi over 4. So if I subtract 2 pi from it, I'm going to get pi over 4, which is exactly going to be equal to this, right? So I know that the sine of 9 pi over 4 is going to be equal to the sine of pi over 4 plus 2 pi, which is also going to be equal to the sine of pi over 4. Now, if you guys know your unit circle, you know that the sine of pi over 4 is going to be equal to the square root of 2 over 2. Awesome. Easy example there. We'll tackle more periodic functions. We'll tackle more Pythagorean identities in class tomorrow. Great chatting with you guys. I'll see you then.